last talk before we actually get to do some fun on the panel, and that is about testing software architecture. So a lot of this material, oops, let me just wire myself back up here. There we go. There. A lot of this material that I'm actually going to be talking about actually comes from two books I recently wrote over the pandemic. The Fundamentals of Software Architecture, which we released in 2020, and then Software Architecture, the Hard Parts, which was released in 2021, very late 2021. Actually, although they were released in the pandemic, the Fundamentals was actually 7 years in the making. Hard Parts was about 3, so it takes a long time to actually write a book. Okay, so my first question is actually, why is testing software architecture so important? And the answer is this right here. So what we see in this picture, of course, is small village. There's a highway bridge crossing between this river and a small car on it. And that bridge represents the structure, very similar to our architectures. And the cars would represent requests going over those. Beautiful. This is fine. But what happens? Slowly those towns, like our systems, start to grow. And that same bridge is now managing a lot more traffic. And as a matter of fact, if we don't pay attention to that structural integrity of that bridge, unfortunately, this will occur. This is why testing software architecture is actually so important. All right. Because I don't think that we actually want this to happen to our systems. No. I'm going to talk a lot about testing architecture, what it means, the different kinds of testing we can do. But I don't like to talk in the abstract. I like to talk in the concrete. So what we're going to do is actually see a real example. And this is actually of a student standardized testing application. This is a system that students in classrooms, and you can notice at the very top here, there's a lot of classrooms at the very top. This is a system where all, let's say, 4th grade, 3rd grade, 10th grade, all take the same test, just to determine I don't know, how good the school is, how good the teachers are, stuff like this. So students sign in, they get a question, they answer that question, and then once they answer it, the next question gets presented to them. Now, in the background, that question is graded, whether they got it correct or not, and then stored in the database. It sounds pretty simple. But in this particular system here, we could actually have upwards to 200,000 students all taking a test, all through Romania at the same time. Or it might be 20. So this does present some challenges. How do we test a system like this? Well, that's actually pretty easy. We write a unit test case for the functionality. And as a matter of fact, here's a particular test right here to test the student sign-in. Let's actually do this, okay? So we're going to actually run this unit test here, and it passed. It passed. Excellent. Fantastic. This is what we do, hopefully, every day. Every hour, that would be even better. Yes, so this is what we're all familiar with. But this is the corresponding architecture of that student test-taking system. Well, how do we test it? I mean, I just showed you a very simple Python unit test to be able to test the functionality. But what does it really mean to test software architecture? that underlying structure to our systems. We don't have to be an architect to test the architecture. That's what I want to show you. Because essentially, what we're really looking for is structural decay. Just like this pylon holding up a highway bridge. We're looking for the cracks and seams within our architecture. So how do we do this? Well, let's take a look at two main ways of testing architecture, separate from the functionality. And as a matter of fact, there's two main processes. First, we can actually test operational characteristics. Those things like scalability, performance, reliability, all of these kind of ability things. That's one type of test that we can execute. But then there's another type of test, and that's the structural integrity of that system, separate from the architecture characteristics. Now, doing this actually allows us to answer some very key questions. First of all, based on either of these two types of tests, which we'll see how to run, first of all, are changes to the functionality that we're continually making in our application, are those impacting the structural integrity of our architecture? Maybe we're not making a lot of functional changes, but maybe it's changes to the environment that are happening. Do those impact any of the structural integrity of our system? And finally, can you actually demonstrate that we are scaling? That the system is elastic? Or that it is responsive? So these are the three things we can do with all these different tests. All right, so let's have some fun and take a look at how to do these kinds of testing. Again, this doesn't have to be an architect to actually execute or even write these kind of tests. So let's take a look at operational characteristics first. This is probably, I would say, the most common type of test we can run to actually determine the structural integrity of our system. By operational characteristics, I'm really talking about these architecture characteristics. Some people call these non-functional quality attributes. Some people call these system quality attributes the abilities. I actually prefer the term architecture characteristics, and I'll tell you why. Because it's been my experience in all of my travels that if you use the term non-functional requirements, well, if I approach, let's say, a product owner or a business stakeholder and say, I'd really like to discuss the non-functional, they're not listening to anything further. It doesn't have to do with the functionality, don't bother me now. System quality attributes tends to imply this after-the-fact polishing that we do on the application before we send it out. And in fact, these are the grounding foundation of our systems. But we have a little problem. What do these mean? How do we define these? And that's one of the issues of architectural characteristics, especially these operational ones. What does scalability actually mean? How do we define it? Now, most of us understand scalability. We define it as the system needs to scale. Responsiveness is an easy one. How do we define that? Well, the system needs to be responsive. And you see the problem. We're just kind of repeating the word. So let me give you a little trick and tip about this. So, what's reliability? We use it all the time. We usually say our systems need to be reliable. You and I know what that means. I know what reliability is, but I'm having trouble defining it. Well, reliability turns out that it's actually what's called a composite characteristic. So here is the magic, everybody. And are you ready? If you can measure it, then you can define it. So whenever I'm looking at an architectural characteristic, some sort of operational characteristic that's really important for this system to have, first thing I say is, okay, how would we measure it? What do you think? How would you measure reliability? What do you think? Any ideas? What would you kind of analyze? What would you measure? Yeah, downtime. Sure. Yeah, systems that kind of are up and down, aren't very reliable. Yeah, and I can measure that. So we've got our first definition of reliability, the amount of uptime. Yeah, which a lot of times we turn into availability. But yeah, we can measure uptime. Absolutely. What else can we measure to see if our system's, quote, reliable? Oh, yeah, the data. Absolutely. If I go and place an order for one of my books, and then I go and review that order, and all of a sudden it's a different book, I'm probably going to order this from somewhere else. Yeah. Is the data consistent? So now we've got data consistency. Maybe even add to that data integrity. Do you see, these are things that we can actually measure and then for us define. So that's the real secret. If we can measure something, we can define it. Let's do another one that's so obvious to all of us, but maybe not. How do we measure scalability? What would that be? What would we measure for scalability? To see if our systems can handle an increased user load. What do you think? What's this? Oh, there was something over here. One more thing. Oh, yes. So we could do synthetic type transactions to actually measure that. We're going to get to those tests. But as we keep adding users, more requests, is the response time impacted? Because the response time should be very consistent. As we merge or acquire another company, do we have capacity in the system? Thread pools, database connections, machine, CPU, memory, threads. Do we have enough capacity for that kind of load? Yeah, these are things we can actually measure. And you know what we just did, which is so cool? We actually just defined scalability. So I love this kind of trick or tip. So, how do you measure these? Well, one popular technique, very nice technique for measuring these, are things called architectural fitness functions. Now, these were first coined in the book Building Evolutionary Architecture, written by my friend Neil Ford and Rebecca Parsons and Patrick Watt. Now, an architectural fitness function is something we write, is some sort of test that we can run that actually objectively measures a particular architectural characteristic. Notice I said objectively measures. This is numerical analysis. That's what a fitness function is. It actually comes from engineering. When we would have a great example on an airplane, on a jet. Did you know that most aircraft, the wings can actually bend almost 90 degrees? Almost. So if you're flying and all of a sudden you're in turbulence and you see the wings going like this, don't worry at all about that. No, they can almost fold straight up. But we want to add, because we're flying back and forth here in Europe a lot, we want to add about 25 more seats right in the middle of the plane. Yes, I've been in that experience. That wasn't pretty. So, sure, let's make the aisle smaller, we'll make the seats smaller, we'll pack things in. But does that extra weight, where it's loaded, impact the bend of those wings? See, in engineering, fitness functions are used all the time. And so now we apply them to architecture. And as a matter of fact, now we can say, okay, so what is a fitness function? It's any sort of tool or product that actually generates metrics, observability, that we can then gather and analyze. A lot of tools, a lot of products, a lot of service orchestrators already gather a lot of these metrics, for example, in microservices. The trick is, what do we do with that information? And it's observing that information, tracking that allows us to measure these. Now, we don't necessarily have to use products, and in most cases, I actually don't. I'll just show you an example of how we can actually write a fitness function. So let's say it starts with our application, our website, service, it doesn't matter, we have a deployment unit, and we're interested in response times. We can stream any sort of metric from there, our uptime, our downtime, the time it took for us to start, the response times. Now, for example, Kubernetes, has all this stuff, yes. But here's my point. I can stream that to a queue, to a message queue, to Kafka, for example. And then I write a capture service. I write a capture service to collect all this information, all that raw data. And then the funnest part is I get to write an analysis service that starts analyzing that data, the trends, or maybe I'm looking for a particular threshold. And it starts just behind the scenes, in production, we don't even know this is going on, starts tracking all of these operational characteristics. But then, when a trend is noticed, or we reach a certain threshold, notify me. Otherwise, just leave me alone, don't bother me. That's the basic model of a fitness function. Okay, fantastic. There are two kinds of fitness functions that we can actually write. Those fitness functions that actually do measure trends. These actually are my favorite. I like these most, but it does depend on what we're actually looking for. If we've got specific SLAs, I care about the trend, but I also care about a particular threshold that we have guaranteed contractually will never go over. So we can write both of these, either or. But the point is, over time, we can see whether changes to our functionality, changes to our environment, or even just to demonstrate that we in fact are scaling. All right. There's one more question, because we're going to look at a whole bunch of different fitness functions. We're going to actually see how to write these. But first, one other question. It becomes a dilemma. Like, when should we actually run these fitness functions? Well, we've got two options. They can either be triggered, which usually runs through a CI/CD pipeline, or they can run continuously in production. Well, which one should I use? And of course, everybody who just took the master class these past 2 days knows exactly the answer to that question. As a matter of fact, I did forget. I was so excited to be here. I was actually going to wear my architecture shirt. I actually do have an architecture shirt. It's a black t-shirt, which I like wearing black t-shirts. And it has two words on it. It depends. I like it because everybody always asks me questions. I just kind of stand there like this. It's like, why aren't you answering my question? Oh, I am. Yeah, it depends. But it depends on what? Because it does depend. Let's take a look at the differences between these. With triggered fitness functions through a CI/CD pipeline, the nice thing is, and the huge advantage, we get to find out if we've impacted something in the structural aspect of our system. This is totally separate from the functionality. This is the structure, like that bridge. We just had a big iteration. Did I impact anything that's really important to us? Did I impact maybe responsiveness? In our testing application, we need high levels of elasticity. We could have 20 users or 20 students taking a test. We could have 200,000 taking a test. Great example of elasticity. Did I impact any of that? I have to have high levels of data integrity, because one of the key things from the education department is that we absolutely cannot lose any data. What's data integrity? Am I impacting any of those things? Can I demonstrate it? These are all examples, and guess what? I could run this in our CI/CD pipeline, and I could find out right away whether we impacted anything. Ah, yes, but who would like to maintain all of those tests? Not it. No, thank you. I don't want to write those. I have to maintain all those tests. And as my functionality changes, I have to start maintaining those tests as well. But I also have to maintain that kind of data volume. If we've got rapid changes, or even changes to all of our data, I'm going to have to re-engineer all of my test data. But you know, it gets a little worse than that, because it's been my experience that it's not very accurate. You see, what we try to do is simulate what the user's going to do. Good luck. With fabricated synthetic data. Well, what ends up happening is because of the type of data I've loaded, maybe it all of a sudden synthetically goes from a row level to a page level to a table level lock. Boom! All of a sudden, at 2,000 users, we're done. Oh, we impacted it. Did we? Is it the fault of what we changed? Or is it the fault of the testing that we're doing? You see, we can generate all these false hotspots in the database. And we're not really simulating the true user behavior. So we can start to see the implications of this. But what about continuous fitness functions? Those that are just running in production continuously in the background all the time. Well, if we do this as a continuous in the background, in production all the time, you start to see that there are no load tests that we have to maintain. As a matter of fact, there's no load data because we're using actual user data, actual user behavior. And as a matter of fact, we are exactly modeling that volume. We're not fabricating a potential hotspot in the database. Oh no, we actually can find it doing this. It's a huge advantage. Also, it allows us to really just continuously run this 24 hours a day and continue to start to see the trends of what's happening when we change our environments, change our functionality, all that kind of stuff. It's fantastic. Oh, but what's the other trade-off? Yeah, all that's great, it's really cheap, but I don't find out about it until after we release our software. Oops, sorry. I guess I know what we're going to be doing on this iteration. Yes. So you kind of see, we have this choice that we need to make. When do we run these operational characteristics fitness functions? And the trade-off really becomes as follows. Here, we get early detection, but it's a lot more effort, and it's not as accurate. Continuous, later detection, but it's pretty cheap. We don't have to maintain anything. And it's a lot more accurate. There's what it boils down to. That's the decision of running continuous or triggered. Oh! Or maybe and. There could be times when you still want to track trends and still have everything, but try to get maybe a little bit of an early detection. Okay, so tell you what. Let's write some of these. Okay, let's go back to our student test taking. Enough abstract stuff. Let's actually write some fitness functions, because I want to show you how straightforward, nothing simple in our industry, but how straightforward these actually really are. So here's exactly what happens, everybody. I'm going to go through the flow of this particular system. So the very first thing happens, the student answers the question. Okay, that comes into this test taker over there. The test taker sends it over to a queue, delivers the next question. Okay. Next thing that happens is that the grader pulls that question or that answer off the queue, and then grades it, determines if it's right or wrong, and then third, stores it in the database. Okay, so that's an easy flow. Let's write a fitness function for data integrity. It is absolutely imperative that we don't lose student answers on any sort of system crash. We can't lose any answers. Okay, let's write that fitness function. We'll go over here. This is kind of testing no data loss. We can call that data integrity. Any ideas of how we can make sure that we're not losing any answers? This one's pretty straightforward. Yeah, we can do a simple checksum, can't we? Observability. I can extract from these services exactly how many student answers were submitted. I have that number. I know exactly how many answers I received in the grader. And finally, number 3, I can actually do a query and find out how many answers were actually stored in the database. Yeah, and I see if they're all equal. That's how easy fitness functions are. Or are not, I should say. Because what's the problem? During a testing cycle, or we may be testing for 6 or 7 hours during the day, these numbers, folks, will never, ever be equal. There's always going to be a lag. So we have to qualify that checksum. And we basically write a fitness function that says, when we get to an idle state, then compare those numbers. Yes, when the queue depth are all 0 for every single one of the queues. When the auto grader basically says, I'm not processing anything. That's the end of the testing cycle. Now we can actually compare them. And this is what actually runs in the background. And you can see we've got all 3 of these metrics. They continue to run, and everything's always the same. Except right here. How would we ever have known that? We wouldn't have. That's what fitness functions do. That's what this testing of the architecture is really doing. Are we losing any questions? And in fact, we did. We did lose some questions, or answers, I should say. And now I have to go and investigate it. Okay. Well, let's do some more interesting ones, though. How about elasticity? How will we measure and ensure that we're not impacting anything from an elastic standpoint? So we have to process 200,000 potentially student answers, perhaps every second. That's a lot. Well, what I can do is actually take a look at the response times. It's a good measure of elasticity, because if the response times remain about the same, regardless of whether it's 20 or 200,000, that really does demonstrate an elastic system. So let's do that. I can actually nothing's easy, fairly straightforward, gather all the response times from the sign-in service, gather the response times from the test taker, and know the number of students. I can also extract that, and then I write a fitness function to compare these two. And as a matter of fact, let's do that. I write that in that analytics service, I run it, and are you ready? This is what that looks like over time. Now, this is a graph, but this is all happening behind the scenes. It's kind of tracking, it's analyzing. It's looking for trends based on a certain time or a certain direction. And what do we notice? Well, here's our average duration of the test taker down below. And there's our number of students that we have at any given time. But if we draw a line across here to get the mean, we notice that everything pretty much is about 1 standard deviation from that mean. That shows a pretty stable, elastic system, except right here. You notice what happened. Now, I'm not observing this. That analytics service, which, by the way, I write a lot of these, and they are fun to write, actually says, whoa, what's going on? Look, this is going up. Our response times are getting worse and worse and worse. But you notice what's happening. We had a couple of classes or a couple of schools immediately sign in and start taking a test. So likely, what was going on here is all of a sudden we said, oh, I need more instances of the test taker service. we've got increased load. So there, all the instances are starting. So the response times start to climb, but here, they all started. And notice it went back down. But we're going to actually explaining why we have that little peak and then a valley, and it got better. Hey, I got a great idea. That's another fitness function that we could actually write. Does anybody see it here? Another thing that has to do with elasticity. As a matter of fact, I've got a good clue about it. And it's all this stuff right exactly here. Because what likely happened? What likely happened was that we were starting more instances. When you think of another fitness function we could write to ensure great levels of elasticity right from that information there. Yeah, how long does it take that service instance to start up? Because if it's too slow, this line is going to go all the way up. Hey, that's a great idea. Let's write that fitness function. So what we can actually do is measure or extract from any of these tools, how long did it take each instance to start up? I can actually, again, observability. That data needs to be available from the service, or from the container, or from the particular orchestrator. So, how long did it take to start it up? And then I write a fitness function to track that based on time. And this, everyone, is exactly what it looks like. Are you ready? Here we go. It's not too bad. And all of a sudden, whoops. Alert. Beep, beep, beep. All of a sudden, it's like, whoops, I'm sorry, I've got and this is embarrassing, right in the middle of a session at a conference, I've got to answer this. Oh, all of a sudden, that analytics service is running in the background suddenly noticed, hey, you have a problem. It's more than double what it was before. Ooh, what happened? We had a new release of that test taker service. And you know what happened? We did something to impact the mean time to start of that service. Is that something you would ever think about testing? Never. Because we're concerned about students sign in, did they get the right question, caching question answers, and all this kind of stuff. No, we don't even think about this. But this is not going to work. So, we fix it, we find the problem, it's like, oh, yeah, I didn't even know about that mean time to start, because these instances have to start up fast. I fixed the problem, and that is now where we see that graph. You know what's cool? This all runs behind the scenes in the word and stuff. But do you see what else the value of these are? I can demonstrate to you, first of all, that we had a problem and that we fixed it. Or I can demonstrate through some of the other analytics and graphs we saw by just saying, hey, generate a graph today. There we go. I can actually take that picture over to a product owner, a stakeholder, anybody, and say, yep, we're doing good here. I can answer that question. Did these major changes to the restructuring impact any of those? No, here they are. It's pretty cool stuff. All right. There is one other thing that might happen in this particular system here, and it would be bad. Do you notice what we've been focusing on so far? It's just been like the sign-in or the test taker. Yeah, those have to be elastic. But what else can you see in this architecture that has to be elastic? Yes, well, the database, absolutely. Yep, because there's our student answers. But what happens if the auto-grader can't keep up? So you're absolutely right. It's related to the database and how fast I could push those answers into that database, do those inserts. Now, I can promise you I don't have 200,000 connections. So it will be slower. So where's my bottleneck going to be? Those queues can all fill up, and all of a sudden, everything stops in the world. Let's measure it. It's another area. So part of this exercise is not just simply writing fitness functions. It's trying to think about the algorithms, where in the system things might go wrong. So let's do that. So I'm going to do a concurrency analysis of the auto grader. Is it keeping up? Well, how can I find that out? These, everyone, are fitness functions. Measurements that I can actually do. Oh, well, what's the number of pending messages? That's just the queue depth. I can find that out right away. And so now I write a fitness function to track that queue depth based on the number of users over time. And this is what happens. Here's my queue depth. And it continues to run, continues to run, continues to run. But do we notice, yeah, it's going to go up and down and up and down, but overall, yeah, that comes pretty much to the mean. Maybe a couple of standard deviations, but not bad. And that's what that analytics service that's actually measuring these things might actually do. It might actually say, what's the mean? What's the standard deviation for every of these data points? And if it starts to go above 3 multiple times, start analyzing a trend on that. And figure out over the course of a certain amount of time, yeah, it's getting worse. It's not keeping up. Yeah. And that's tuning to the auto grader. So these are all the operational characteristics. These are what fitness functions are. There's so many companies that are using these fitness functions, and we keep saying, these are great, but how do I write them? What are they actually? Well, we've just seen them. But you know, there's another thing we can actually measure and test in software architecture, and that's the structural integrity of our system. So here's all my components. They're usually manifested through a directory structure. And so I've got order placement. I've got to place an order. I've got inventory management. When I place that order, now inventory, email, item pricing, and supplier ordering. All this needs to happen when I place an order. Now these are all just simple method calls, object instantiations and stuff. But let me ask you this, is it my responsibility to decrement inventory? No, of course not. It's inventory management, instantiate a class, invoke a method. How about email? Nope, I have no idea as order placement how to do an email. Fine. So I'm going to ask you, send an email. Well, if our inventory goes too low, now I need to order more from the supplier. But it's not my responsibility, it's yours. And finally, we increase the unit price if inventory goes too low. Is that my responsibility as order placement? No, of course not. It's item pricings. I don't do that. Well, that, everyone, is the standard roles and responsibility model. Okay. Does anybody see a problem with the structural aspect of this system? These are not class files. These are components that contain classes. Things the application does. Anybody see an issue? It might even be services. Yeah, it's right here. Yeah, that's highly coupled, isn't it? Yeah, this is not going to be that easy to maintain. So, how do I decouple the system? Well, that's something to decouple systems, to create looser coupled systems. It's something called the law of the meter, also known as the principle of loose knowledge. The law of the meter comes from the goddess of the meter. The goddess of the meter was the goddess of agriculture. She produced all the grains for everybody in the world. But she had no idea what she did with them, and she didn't care. I've got one job, no other knowledge. And this is the law of the meter, that a service or a component should have limited knowledge about other services or components. So let's apply the law of the meter here. Is it my responsibility to order more stock right here? No. No, that's supplier ordering. Let's apply the law of the meter. Should it even be my knowledge that that needs to happen? No. Can I defer it to somebody else? Yes, I can. I can push it down to another component, inventory management. Now notice what I just did. I just applied the law of the meter. Are you ready? Less knowledge, hence less coupling. You see, this is where the roles and responsibility principle falls apart when we try to create loosely coupled systems. Because it wasn't my responsibility, but I shouldn't even know about that. Hey, how about increasing the unit price right here? Is that mine? No. Should I even know that it needs to happen? No. Can I push it anywhere further? Yeah, inventory management. But look what I've done. I've just applied the loft meter and I've decoupled that component. I continue to push these things down until the only people I'm talking to are my close friends, my relatives. That's inventory and email. Because I can't defer that knowledge to anybody else. So that's what the loft meter is. So now I decouple it. Guess what's going to happen next week? Oh, somebody's going to go and call something else. So how do I enforce this aspect of structural integrity? Here's how. Do this through other types of fitness functions. Things, for example, like ArcUnit in Java, ArcUnit Net for .NET, NetArcTest also in .NET, and SonarGraph, which does this for Java, C#, C++, C, Python, JavaScript. So I can actually codify my structural integrity rules. This is what it looks like. For example, I want to make sure that no one links order placement to anything else. Look, this is what that looks like. That's the actual executed class file or method. Look at the method name. Placement can only access notification and inventory. So, classes that reside in a package placement should only access classes that reside in a package notification. These are cool tools that are free, folks. These are free, that you can actually now measure the structural integrity of your system. Things like this. Let me back up one. Let me show you one more. Only the business and services layer can access the persistence layer. In other words, presentation can't talk directly to the database. Yeah. What's the very first thing any user interface developer will do that's worth their weight in, or worth a grain of salt? Yeah, they're going to go directly to the database because it's faster. I'm not going to go through all that with layers. I'm just going to make my queries. How do we govern all that stuff? Like this. We write a test. For example, no classes that reside in a package presentation should access classes that reside in a package persistence. And knowing that this will happen, I always use because clause. Because when this fails, now the developer knows exactly why it failed and what those integrity constraints are. This is cool stuff. As a matter of fact, this is the same thing in C# for .NET. Types in the current domain that reside in the namespace presentation should not have a dependency on my app.presentation or persistence. Yeah, these are really cool tests. All right. Let me show you one more because I just love this one. Because this last test right here, actually, you can describe your entire architecture. Whether you're using a modular monolith, whether you're using microkernel, whether you're using a large service, you can do this with this. Now, this really defines the layer architecture, but it's extensible to use it for a modular monolith as well. So, layered architecture, there we go. Describe it for me. Okay, well it has 4 layers. How do I know? Because there's the logical layer that I'm going to use in my test, and there's the actual namespace, or package structure, or directory, where that layer represents. Now, I can say this. Here's my constraint rules. This layer can only talk to that layer. This layer can't talk to this layer. If I was using a modular monolith in a domain partitioned system, I would simply use layer here as domain. So one domain can't talk to the other. It's actually really cool stuff. But that's what I mean about testing software architecture. We test software, everybody, all the time. This is a call to action. These tools exist. Most of them are free. Most of them you don't know that you actually have already in your infrastructure. We can use these to test the structural integrity and the operational characteristics to ensure that this doesn't happen. Make sure that your systems, that structure, that architecture is tested just as much as your functionality. Because if you don't, this will in fact happen to you. Thank you so much.